Hey everybody, I'm back with part 2 of fitting models to data. And in the last video, we did a recap of classical and mechanistic epidemiology. And we talked a little bit about why fitting models to data is important. Next, we're going to do a quick review of linear regression. So here's an example. We start with a question. How does hookworm burden affect blood loss? And the first thing that we would do is collect some data. And rule number 1 of statistics, always look at your data. And so here's hookworm burden on the x-axis and daily blood loss. And right away, it looks like a line would fit these data reasonably well. So that's something that we might want to do. But there isn't our only model choice option, for example. Is there a relationship? Suppose hookworm burden wasn't associated with daily blood loss. We might just use as our best guess for what daily blood loss is going to be, just the average. And that's exactly what we're doing here. And we could ask ourselves, is this a good fit? Is this a good model? And one of the ways that we assess whether or not a model is a good fit is to look at the errors. In particular, in statistics, we look at residuals. Residuals is another name for the error. You can think of them as the same thing. And we often look at the residual, we square it, so we don't have to deal with negative values, and then we add all of those up. So how far away is this point from the candidate model? Square that value, and then add them all up. And that represents the overall error associated with the model. A good model, that overall quantity, the sum of the squared errors, that'll be small. And when you fit a regression line to a scatter plot, that's what you're doing. You're minimizing the sum of the squared errors. It's called least squares fitting, which I think most people are probably familiar with. So we want to minimize the sum of the squared residuals. And so we can choose an intercept and a slope in such a way that the intercept and slope that we choose minimizes that quantity. And it turns out that's a fairly straightforward calculus problem. We won't go through that here. But if we think that a line's a better model, we can see we can reduce the residuals by quite a bit. If you just compare those two, we have long lines. If we square those and add them all up, we're going to get a big number compared to this model. It looks like it fits much better. And this line is actually the line of best fit. And so hookworm burden is our X variable. Expected daily blood loss is the response. And then we have the intercept term and a slope term, the effective hookworm burden on blood loss. And we also have this error term here, and we make some assumptions about what that error term looks like. Usually, for simple linear regression, we assume that it's normally distributed. For example, residuals are normally distributed. More on that in just a second. But this is called least squares fitting. It's not the only option that we have in order to fit these lines to the data. Another option we could investigate is maximum likelihood. So what maximum likelihood attempts to do is figure out what the probability of the observed data is given a particular model. So what's the probability that we would see data like the data that we're seeing if we set these parameters to a specific set of values? So imagine setting our parameters to a specific set of values and then assuming something about this. Usually we assume that it's normally distributed. We can use the density function from a normal distribution to actually figure out what's the probability that we would see a value like this. And then to get the overall probability of the data, we would just assume that their observations are independent. We can multiply all those probabilities together. And that would represent sort of the overall probability. And the idea between maximum likelihood is we want to pick the set of parameters that maximizes that likelihood of seeing data like this. So you can think of likelihood as a conditional probability. It's the probability of getting data like this given a specific set of parameters. So much more on this in coming up when we talk more about likelihood as it pertains to SIR models or dynamic models. But I just wanted to point out that's another option that we have. So once that we fit the model, we can ask questions like, is the maybe the slope, our estimated value is really not different from 0, and this is plausible just by chance. We can do hypothesis testing. And so in classical hypothesis testing, what we're really doing is we're asking, is this value 0? Is it a plausible parameter value? And we test that idea. And so we observed a slope of 0.04. Well, that's what we observed. Is it plausible that it could be 0? We do a hypothesis test. We find out what's the probability of getting a slope at least as big or bigger than the one that we actually observed, assuming this null value. And that's what a p-value is. And here it's very, very small. Small p-values are evidence against a null hypothesis. And so what we conclude is, these data are not consistent with the null hypothesis, and we would end up rejecting the null hypothesis. So this is all, statistics 101, but we can also get confidence intervals for the parameter value. What confidence intervals are really a collection of plausible parameter values. And so one way to get confidence intervals, you probably remember from statistics, is using standard error and a z-score, a z-table, to get a 95% confidence interval. But there are other ways to get confidence intervals. Another way to do it is to propose candidate values for the parameter and do a hypothesis test. What you're really asking here when you do this test is this quantity a plausible value? If it is, it belongs in the confidence interval. And so you could continually test lots and lots of values and get a range of plausible values. Here we can see 0 is not a plausible value. We rejected that null hypothesis. That's why it's not in our confidence interval. If we instead tested this slope as being something like 0.03, we would end up not rejecting the null hypothesis, and we would conclude that it is a plausible value. That's why it shows up in this interval. So there's a relationship between confidence intervals and doing a two-sided hypothesis test. So that's another way to get a confidence interval. You always want to make sure that the conditions for linear regression are satisfied. And so I like to think of these, there's a nice mnemonic, lines. So linearity, independence, normality, and equal variability. Those spell out the word line. And then S, I like to think of that as the data representative. They were collected via simple random sample or something along those lines. A probability model was used. And so we want to check normality. The residuals should be normally distributed. That's one of the conditions. It's one of our assumptions when we did a linear regression model. And with such few data points, it's hard to get a good sense. But this, it doesn't look like there are any extreme observations. It looks bell-shaped. So we might be convinced that the residuals, there's no strong evidence that they're not normally distributed. Linearity, we can do something called a residual versus fitted plot. It's a common diagnostic plot. And to assess this linearity condition, well, for one, you can look at the scatter plot and look to see if it's roughly linear. But doing an RVF plot often reveals potential nonlinear patterns that you can't see just by looking at a scatter plot. And so what you're looking for, weird shapes like a rainbow shape, any strong evidence of nonlinearity. What you hope to see is just an even band of points. The same number above is the same number below this line at 0. And again, we don't have a lot of data, but based on this, not any strong evidence of any weird shapes. Independence, you really have to think about how the data were collected. Are our responses independent from each other? So that's not something that you can usually check just from diagnostic plots. And then constant variability. So if we go back and look, these all come from this condition here where we're assuming that the errors are normally distributed. So this sigma doesn't change. That's one of the things that we're assuming that we require for our conclusions about linear regression to be valid. And again, you want to see an even band, no evidence, no megaphone shapes or any weird thing like that. And then we can still ask, do we think it's a good model? And so there are lots of different metrics, lots of different things that we can investigate to see if our model is a good one. So R squared is a nice one. It explains how much of the variability in the response is explained by the model. So high R squareds are better. We can do a chi-squared goodness of fit test. And so usually there you're comparing to see if your model fits at least as good as a model that's perfect, for example. A likelihood ratio test or a nested F test, for example, a drop-in deviance test, sometimes it's also called for simple linear regression. The null hypothesis is the simple model does just as good of a job as a more complex model. And so usually this is done, if you do it at ANOVA, it's an F test, or if you do something like logistic regression, sometimes they refer to it as a G test, you're using deviance instead of sums of squared residuals. And then the AIC, this is information criteria. This is a way to compare models that are of different sizes. And so it adds a penalizing factor for complexity. So that's a good way to compare models that have a different number of variables in them. And then cross-validation, can the model predict well outside of the fitted data? This is really key in guarding against overfitting a model. What do I mean by overfitting? So back to the opening question I asked, do you think that that model that was fit to these data is a good one? And if, well, maybe you should just think about that now, although it's on a slide that says overfitting, so maybe the cat's out of the bag. But yeah, here, this is a classic example of a model that's been overfit to the data. And so you could keep adding terms to a model. Eventually, you can make it fit perfectly. But that's really, what you're doing when you're overfitting is you're fitting the noise, right? This really isn't the underlying process that's driving these data. Instead, much more likely, it's probably some underlying process that looks like this, right? And maybe that's the right model to have fit to these data. This other model, the green line, is overfitting. And so you can guard against overfitting by doing cross-validation. So how well would your model do is if it was presented with new data that was generated from the same underlying processes. Usually what happens as you add complexity to a model, you start to reduce the bias, but the overall variability in the process increases. And so that's the bias variance trade-off. So usually they're opposing forces. So a simpler model, there's less variability in the model building process when it's fit to new data, but the bias is higher. And so there's sort of a sweet spot in between where you've minimized both bias and variance. Let's move on. And colinearity is also another consideration when you're looking at models. If you have variables that vary with each other, or if they're highly correlated, or a subset of variables that's highly correlated with a variable, you can get unpredictable results, and especially if it's a strong colinearity. Non-identifiability, again, another thing that we need to watch out for when we're fitting models to data and model building. And so this just means that different parameter sets fit just as well. And so in the context of dynamic models, maybe we have a transmission parameter and a recovery parameter. But maybe we have different sets of those that fit a particular model just as well. And so then we don't know, we can't definitively say which parameter set is better. That's the non-identifiability problem. And so that As a good overview of fitting statistical models, we asked a question about a relationship, so daily blood loss and hookworm burden. We made some observations, we collected some data, and we created a scatter plot. We chose to fit a line to the data. And we asked how well does it fit? Does the line do a pretty good job? And we answer some research questions. Is the slope significantly different from zero? Is zero a plausible value for the slope? And we found pretty strong evidence that no, zero was not a plausible value. And we actually came up with a range of plausible values. That was our confidence interval. And we learned something, hopefully. And so that should be, all of those things that we just talked about should be familiar to you. Next, what I want to talk about is maximum likelihood and take a closer look at what actually happens when we do maximum likelihood estimation. And then how does it fit in when we apply it to dynamic models?